We on now? Okay, Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon to the participants of this distinguished lecture series, number 51, organized by the Faculty of UTM, Faculty of Engineering UTM. So this afternoon, we have Professor Carlos Guedes Soares, who is a distinguished professor from the University of Lisbon, Portugal. He will deliver a lecture entitled Prospects for Autonomous Shipping. Very interesting topic. Theoretically, it's possible to have autonomous ships with modern technology. However, whether it is practical or not, so Professor Soares will enlighten us on this. We have known Professor Soares for quite some time now. He's a well-renowned professor internationally. I met in a few occasions in conferences in Europe and US. And also, at the moment, we have a collaboration with Professor Soares under the Horizon 2020 project. A number of our lecturers has attended this center at the University of Lisbon. So hopefully we will continue our collaboration in the future. So before we begin, I would hand over to our dean, Professor Muhammad Rafiq bin Abdul Qadir, to briefly introduce Professor Soares to our audience. Please, Professor Rafiq.
Professor Adi Maimun, thank you very much for moderating the session. Assalamualaikum warahmatullahi wabarakatuh. And welcome everyone. Welcome to our 51st UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Carlos Guedes Soares from University of Lisbon, Portugal. A bit about our distinguished speaker today. Professor Carlos Guedes Soares is a distinguished professor of the Engineering Faculty, Instituto Superior Técnico of the University of Lisbon, and the head of the Center for Marine Technology and Ocean Engineering, CENTEC, which is a research center of the University of Lisbon that is rated as excellent and funded by the Portuguese Foundation for Science and Technology. He received the M.Sc and Ocean Engineer degrees from the Massachusetts Institute of Technology, MIT, USA in 1976, the Ph.D. degree from the Norwegian Institute of Technology of the University of Trondheim in 1984, and the Doctor of Science degree from the Technical University of Lisbon, Portugal in 1991. He has supervised more than 55 PhD students and has co-authored more than 700 journal papers and several more in conferences. He has a H index of 58 in Web of Science, 70 in Scopus, and more than 18,000 citations and 26,000 in Scopus. He has been publishing in probabilistic modeling and uncertainty analysis applied to different problems involving hydrodynamics and structural analysis of floating and fixed structures at sea. He has been coordinating the Symposium on Structure, Safety and Reliability of the Ocean, Offshore and Arctic Engineering OMAE conference since 1989 and has been chair or co-chair of various conferences in the series of OMAE, ESREL, IMAM, MASTRAC, MARTEC, RENEW, and ICCGS conferences. He has been the editor and now the editor-in-chief of the Reliability Engineering and System Safety Journal, RESS, since 1992. He is co-editor-in-chief of the Journal of Marine Science and Application, and he belongs to the editorial board member of about 15 journals. He is a fellow of SNAME, the Royal Institute of Naval Architecture, RINA, IMarEST, ASME, Ordem dos Engenheiros, member of ASCE, AGU, and SRA, and a member of the Portuguese Academy of Engineering. So that is a brief biography of our distinguished speaker. Here now is Professor Carlos Guedes Soares from the University of Lisbon, Portugal, on the prospects for autonomous shipping. Professor Carlos Guedes Soares, over to you.
Well, good afternoon. Thank you for your introduction, Professor Rafid and Professor Adi. It is my great pleasure to have the opportunity to be included in your distinguished lecture series. Our contacts with the UTM have already started several years ago. I was lucky to have had the opportunity of visiting Johor Bahru few times, enjoying the local environment and getting to know the faculty and especially the Department of Ocean Engineering. We also had guests from that department, from that university in Lisbon visiting us. So we have had some collaboration in the past, and therefore this opportunity of being in touch with you is most welcome. I will be talking on prospects of autonomous shipping. This is a topic of a very actual topic that has kept the attention of the industry. I hope now you have been able to see the introductory slide with the indication of the title of my talk.
Yes, Prof, we can see the slide. Thank you.
Very good. Thank you very much. So I think I can proceed. My lecture is a generic one, trying to bring the main points that are being discussed and that are involved in this problem, which is a very complex one that has different implications in the shipping and in the maritime industry. So I will be talking generally on the existing autonomous ships and the remotely controlled, and we will discuss the differences. Then I will discuss the main aspect of the autonomous ship, which is the path planning and guidance. So this is the main technological aspect that will bring the ship from one place to the other. And then I will address related aspects of safety and economy, which are important aspects that can motivate or can allow this concept to go ahead, or it can hinder it from progress. So those will be the main topics, and I will then start by recognizing that autonomous ships have been in the last several years in development in different research projects that involve companies and universities. You are surely aware of the developments that have been made in autonomous vehicles. So small vehicles, both surface vehicles and underwater vehicles that have been under development, and this has allowed the development of the basic technology for navigation, which now is being considered for this next step in size of being the autonomous ships. For the operation of these ships, there are two limiting situations. We can have a remotely operated ship, which is an unmanned ship that has a remote operator that is controlling it. Or we have the other extreme, which has no intervention of humans, and a computer will control all the activity in the ship. So those are the two limiting modes of operation of an unmanned ship. Now, we have several problems to discuss, as I indicated earlier. There is the technical problem. So the question is whether we have the necessary technology to be able to promote the autonomous ships. The other is the social and legal one, which looks at the safety level, because the public will not accept to have ships that have a lower safety level than the present-day manned ships. And then there is the economical level, because the ship owners will not be deciding to operate a ship that is more expensive than the present manned ships. So we have to look at all these three aspects. Now, it is important to start making some distinction between what is autonomy and what is automation. So autonomy is the ability of a system to make decisions, to adapt to unplanned circumstances, and to be able to achieve what is expected from the system. So these decisions will be made from supervising agents within the system. Automation is simply to substitute a task that has been executed formerly by humans, which now will be executed by a technical system. So obviously, an autonomous system must be automated, but an automated system is not necessarily autonomous. And the other aspect that we need to consider also is that there may be different levels of autonomy, different levels of automation, which refer to the degree of automation that is implemented in the ship. In general, we will think that the autonomous ship operate with a dynamic autonomy, in which this level of autonomy is adjusted depending on a number of parameters that include the state of the ship, the weather conditions, the traffic density, the distance from the coast or for the port. And the basic idea is that the ships will be autonomous when they are performing simple tasks. But when the situations become complex, then it is necessary that the human is supervising what the system is doing, and eventually is controlling it remotely in those conditions. So autonomous ships always require a monitoring and control center on shore. You certainly see immediately the parallel situation with flights, which we in the last few months we have not been able to travel and to fly, but aircrafts, transportation aircrafts normally operate with control mechanisms, but for landing and starting the flight, then there is manual control. So this is a parallel to what is expected to be done in ships. Now, the technologies for autonomous navigation, which are the main aspect that we require, are available. And in the case of the ship, there are some advantages compared to other autonomous vehicles. like cars and airplanes, which also are moving in direction of autonomy or partial autonomy. So ships have low speeds, and this gives more time to interpret the sensor data and to react on it. The requirements for ship maneuvering are appearing slowly, so it also gives time. In general, the ship has at sea is not confined to roads, to limited areas like a car. Although in some cases we have traffic separation lanes, and in those cases the ships have to go through a lane, or which is a type of a road. There are several options to collision avoidance, and in general there is less traffic density with ships than with cars. The disadvantages is that the inertia of a ship is much larger. It is very difficult to maneuver and to stop a ship, and the communications can be difficult. Now, the main technologies for autonomous navigation are available, and although they need some development and adaptation for autonomous ships. Typically, the long-range situation is controlled by the ship radar, and then in manned ships, the short range is done by humans that observe the short range. In moving to autonomous ships, we have to use cameras to identify the objects and short range radars. And there is also under investigation the use of LiDAR with cameras and radars. So these are the areas that are under development for the autonomous operation. We have then to process all this data to identify all the obstacles that are at short range. And then with the information from GPS and the inertial sensors, then we have the position of the ship, which then can be related to the electronic charts and decide how to navigate and eventually also to avoid collisions if we have short-range obstacles. So as I say, we have technology available. It is the short-range visualization, identification of the targets that still needs some further development. Now, what are the drivers that are promoting autonomous shipping? Well, the advances in guidance and control of the small autonomous vehicles provides the knowledge of the technology for moving the ship. We have also the problem that maritime safety is very much related with accidents that are caused by human error. So there is this idea that substituting the human by a machine, we will have less errors and then we will have a safer environment. There has also been an increasing difficulty in hiring competent crew for the ships. The life on board is more harsh than living in a big city center. So there has been less incentive for people to choose that profession. Also, the manning on board is an important part of the cost of operation. So shipping companies have an economic incentive to reduce manning. And in general, the reduction of overall costs of maritime transportation is a trend that looks at autonomous shipping because of this idea that reducing costs with the crew would lead to a more economic operation. The drawbacks and the difficulties in promoting autonomous shipping is that there will be higher costs of additional equipment. Control, communication, and this type of equipment must be put on board. There must be redundancies, and this will be costs. With so much equipment, the equipment also has probabilities of failure. So the ship will also be prone to accidents due to equipment failure or malfunction. And this will compete with the human errors of the manned situation. Autonomy will also require to have onshore monitoring centers manned 24 hours. And this represents additional costs in establishing these centers and in manning the centers with the crew. Furthermore, to keep the safety of maritime traffic, there are being considered that probably there must be separate safe lanes for these autonomous ships in the approaches to land and ports when the traffic is higher. So this must be created to make sure that there is a separation between autonomous ships and manned ships. Finally, autonomous ships will be prone to cybersecurity. They will be prone to cyber attacks. And therefore, this is another area that needs special attention and, of course, investment to make sure that we have ships prone to that. So how is the industry looking at this? Well, as you could imagine, equipment manufacturers are the main driving force. So this would need more equipment, and this would be very good for the equipment manufacturing industry. Now, seafarers are profoundly opposed to this idea, as it happens in all industries where we see increased automation. There will be a big resistance in this direction. Ship owners have been very quiet. On one hand, I think they are not convinced that this will be an economic success. And on the other hand, I think they don't want to create frictions with their seafarers, advocating a solution that is not welcome by them. The insurance companies are still not sure what is the safety level and how they will insure this type of vessels. If we move to autonomous ships, then the charter contracts have to be revised, and the legal framework for the operation of these ships will need to be revised very much. So IMO, which is the International Maritime Organization, is already started to work on this topic, looking at specific regulations to apply to autonomous ships. However, in general, shipping industry is somewhat conservative, and it may take some time before they are ready to really change the paradigm from manned ships to autonomous ships. Now, there are some concepts already available that have been developed in these research projects, and so there are designs of that goes from small ships like this one for activities like offshore energy and aquaculture support, to larger ships like container ships, bulk carriers, that have been designed and are being studied. We also have demonstrators that have been testing some of the technologies. This is an example that was developed in this project on advanced autonomous waterborne applications. It is a double-ended ferry that uses radar, visual and thermal cameras and LiDAR. As I had indicated earlier, one of the challenges here is the short distance identification, and this is exactly what has been tested in this ship in bad weather conditions. Also in Norway, there has been testing in Trondheim fjord. The autonomous vehicles have been tested to demonstrate their capabilities. I think presently the largest demonstrated is the Birkeland. This is a container ship that has been developed to transport fertilizer from an inland plant to deep sea ports in a distance of around 30 nautical miles. It is 80 meters long and it carries 120 containers, TEU. This ship has already been built. It was launched in February 2020 in Romania, and you see him. This is the model test. This is the ship as built. Although because of the pandemics, it has not been progressed much since this period. But as you see, we have a demonstrator of 80 meters, a container ship already on the way. Okay, so those are the technology aspects and how far we have arrived with the technology. We have already built one ship like that. Now, the other aspects that need to be considered is the safety, as I have indicated earlier. And the main concern is that autonomous ship must be as safe and reliable so that it can be accepted by the regulatory bodies and by the public. The public may even demand that autonomous ships have a better safety performance than conventional ships, in the sense that why changing if we are not changing to a better product? So it is necessary to demonstrate that the systems will not lead to an increased level of risk, in particular to loss of life, damage to the environment, or damage to the assets. And there are some main challenges in this. The one aspect is that now in the risk assessment, we have to include software, because now the ship will all be controlled with software that will control all the control equipments and everything else. We have to assess what is the role of the human operators in the shore-based. How do they interfere with the safety? And what happens in the dynamic environments, so when we have bad weather and heavy traffic. We had an international consortium in a project that has looked into this, and they summarized the safety and security considerations that need to be considered for assessing the risk in the autonomous ship operations. This is the reliability of safety critical equipment, the validation of the communication technology, equipment and software, the maintenance aspects related to the reliability of mechanical equipment, the monitoring of the remote operation by human operators, all the security aspects, in particular cybersecurity, and how we do the management of emergencies with remote operators. So these are the challenges that need to be addressed, and later in this presentation I will address them in a slightly more detail. On the economic front, which are the other aspect that needs to be considered, we need more control equipment for the crew. However, we do not need onboard equipment for supporting the crew on board, and we also save energy that is needed for that support equipment. This also allows to have more space that can be used for transportation of cargo. However, we may need to use better quality fuel to avoid difficulties in operation. We will have extra costs on shore monitoring and extra courses for operating the shore monitoring center. So we have to balance all these different costs and check if the operation will be profitable and therefore attractive to ship owners. So I hope I have given you a general overview on the problem area, and the constraints of both safety and economy. And now I was planning to go relatively quickly through the technological aspects of the main part, which is the path planning and guidance of the autonomous vehicles. So first of all, let's clarify what is the motion planning, which is the starting point. We have a path planning that identifies the path that needs to be followed from the initial point to the final point, and this is defining waypoints that need to be connected. And then we have a path manager that will connect these waypoints with straight lines or curved lines. So we have the control architecture of the autonomous vessel. It has the path planning that uses the map, the destination, and the identification of the static obstacles, and then defines the waypoints that will bring from one point to the other. This gives information to the path manager that then defines the path that connects the waypoints and then passes the information to the guidance system that follows the path by defining what is the speed, the heading, and the commands that need to be taken. The autopilot then makes sure that the heading of the ship is such as to follow the path, and then the autonomous vessel will be acted by external disturbances like wind, wave, and current, and these external disturbances will move him out of the path. So we have a state estimator based on onboard sensors that checks the position and then feeds back to the system to check whether it is on position or it needs correction. So those are the main elements of the architecture to ensure that we have the ship following the desired path. We have then the path planning and the trajectory are concepts that are related. The path is just based on kinematic specifications, so it just gives the geometry of the points where the ship has to go by, and the trajectory is the path plus the assigned time at which the points have to be passed. So the trajectory planning, in fact, has the path planning plus the control of the propulsion system to make sure that the velocity of the ship is such that the time is observed in those points. So in general, motion planning is used both for path planning and for trajectory planning, knowing that trajectory is a wider concept and path planning is sort of a subset of the trajectory. There are many techniques to identify the path. I will just mention a couple of them. The Voronoi graphs has been used, and the idea is that if we have a set of obstacles that are fixed, and if we want to go through them, then the safest path is to keep the same distance from both obstacles. So this would be the safest between these two. Then if we want to go through these two, then this would be the safest, the half distance between them. This would be the half distance between them. And therefore, the ship would go in a path like that to keep the largest distance away from stationary graphs. So we see an example here where the path has been, different paths have been possible, and then an optimization algorithm will choose the minimum cost path between the 2 points, which then in this case is this one. Here is a realistic example done in Norway, in which this technique was used, and you see the path that was chosen between these 2 points. These are the elements of the graph. These are the waypoints in red, but we don't need all of them, so only these green ones then are chosen as the main waypoints. You see them here. So these are the points that have to be followed by the ship as determined by that. We can apply this for different criteria. Here the criteria was the distance to land and also the depth constraints. So for ships with a large draft, then we have to check what is the depth. If a ship has a low draft and there are no depth constraints, then the algorithm would give this other path which goes closer to land, and it's a different one. So you see that this is a technique that can be used in realistic cases and produces results like that, the path that is then identified by those waypoints. Another alternative that is also used to go from one departure to one arrival point is to consider all possible directions that one can go from here. So the space is discretized at a given number of directions, and all these possible paths are considered. After a certain time, the ship would be in these different positions depending on the direction, and then another path would be chosen, and these paths that would go through obstacles will be eliminated, and only the ones that do not go through the obstacles will be chosen. And this then would allow different paths to be chosen, and an algorithm then can be used to optimize. So basically, the so-called Dijkstra algorithm has been very much used here, as in many other transportation problems. So we would have a network with the weights associated with the distances or the time necessary to go from one point to the other. And then an optimization algorithm would choose the path that would have the best performance going from one point to the other. I'll give you an example on a ship weather routing system that uses this type of approach, the Dijkstra algorithm. So weather routing is a more advanced situation in which, in addition to the static obstacles, we also consider the dynamic aspects of the weather, which then we use the storms as being obstacles that the ship also wants to avoid. So we see an example of a transatlantic passage of a container ship that goes from here to the States, and we have two different strategies. One is the regular one, and this is the low speed for the low steaming alternative with a lower speed to save the oil, and we see the development of the storms, and we see that there was a change of course here, avoiding that storm. And finally, we also see another one, and we see that this one, after this time, reached further than this lower steaming, avoiding the bad weather. We have also an example in more coastal type of traffic. So we have in the Mediterranean, we have a fishing vessel that is starting from here. Here it chooses the safest route. Here it chooses the fastest route, and you see that the safest one, he went around the islands. The duration constraint, he crossed between the islands to have a shorter trail, and then after some time, this has managed to be further down because it was duration constraint. So we have these algorithms that allow us to determine what are the best paths to be followed by the ships, and this is the starting point then. Now, having the path defined, we have the guidance system who takes the ship through that path. The guidance system starts from a measured position and velocity, knowing where the ship is, and then he wants to arrive to a desired position and to a given velocity. So it uses information from the weather, from the fleet, from all those basic information, and then sends signals to the controller that then allocates the sensors, the actuators, which in the case of the ship will be the rudder to control the heading, and the propulsion to control the speed. And then we have the navigation system that identifies the position of the ship and then feedbacks the position and the situation, so that we have a feedback loop here to control the system. And in this way, then we make sure that the ship follows the path that has been defined by our path planner. So we have two main aspects. We have the attitude control and the path following control. The attitude control is the autopilot that controls the heading of the ship. And then we have the other motions, which are the roll and pitch, which are the rotations around the longitudinal and the transverse axis, which we would like to be zero, so no balance of the ship. But often they are uncontrolled, so the ship will roll and pitch as depending on the weather. And then the path following control is what keeps the craft on the path. So it uses the weather routing program to give the trajectory, which then controls the autopilot that controls the actuators on the ship. And then we have the navigation equipment to check the position. So we have the guidance system, the control, and the navigation system. So in general, we work with paths generated by waypoints. We have several points that need to be followed. We also have information data on about wind, waves, and current that is also available. We have geographical data about water depth, the islands that are included, and this will be the information on the obstacles that are static and that must be avoided. However, we also need to have a dynamic aspect relating to collision avoidance, because we have traffic, so we have moving vessels that may be close to our vessel, and we have to make sure that then we avoid these vessels, and then we come back to the waypoints. So collision avoidance is also an important aspect that needs to be considered in autonomous vehicles. The path following strategy, the most common one is the so-called line of sight. The idea is that if you are on a ship and you want to follow a certain path, you look at as far as you can see in the horizon, and then you head the ship towards that. So this is the most frequent method that has been used. What happens is that if the ship is very much out of track, then using this type of guidance, you can go in a direction perpendicular to the track to get to the track as fast as possible, and this loses energy, is not very efficient. So recently, an alternative guidance law has been proposed, which is the vector field that defines a vector field that, depending on the position of the ship, that will take it to the path. Here is a straight path, here is a curved path. This is a guidance law that is very much used in aeronautics, where we have a three-dimensional situation, and has been adapted to surface vessels, showing that it has a good performance. So those are the two main guidance laws that I would like to bring your attention to. So as I said earlier, we need to handle collision avoidance very seriously, because those are the dynamic aspects that appear and need to be avoided. So typically, to do that, we need to have an intelligent navigation system, which has to have a module for vessel monitoring and information system, which is a system that identifies all the target vessels that are in nearby, and then tracks what are the motion of these vessels to identify if any of them are in collision course. Then we need to have a collision avoidance system, which then makes the ship avoid the collision with any target that is at collision course. And then, of course, we need the autonomous navigation system to define the course and speed control in the avoidance of collision. So this vessel monitoring and information system very often works based on artificial intelligence. We have the vessel detection and tracking. Neural networks are often used to identify what kind of vessel are coming and what is the track it is following. We also have to estimate what is the trajectory of these target vessels and to predict where will be their future trajectory, and this can be made by an extended Kalman filter. And eventually, if there are communication module, this will help to force the communication between vessels to help to make sure that the vessels will be taking measures to avoid collisions. The collision avoidance system also has the communication module itself, and then it has a decision-making module that makes decisions to change course and speed to avoid the collision with the ship. And in a complicated traffic situation where there are several targets, this decision must be sequential because it has to be done for the various targets, avoiding one and the second and the third, and Bayesian networks have been used to do that. And we have also a collision risk assessment that, based on the identification of the tracks of the target vessel, then decides when it should be necessary to avoid the collision. The avoidance of collision has to follow the rules of the maritime traffic. These are the collision regulations, COLREG as they are called. And if this is our vessel and if this is the incoming vessel, then depending on the relative position between them, then there are rules about what should both vessels do. I think we are all familiar with the rules that exist for traffic with cars. You know, when you have to yield the priority to other vehicles, and these rules are the same. So the collision avoidance module has to follow this type of rules in deciding what action to take depending on the relative position of the vessels. All right, so I think I have given you a very quick overview on the technology and on the main modules that the ship needs to have to make sure that it does the autonomous navigation. Now I will address quickly the aspects of safety and of economy which need to be considered. Safety of the maritime traffic can now be monitored using the automatic identification systems, which is a tracking system that now ships of a given size have to have on board. Ships will be transmitting periodically, every 2 to 10 seconds, information on their position, heading, and so forth. And this will allow centers that collect this information to have an overview of the traffic worldwide. You see here the traffic indicated with the routes where you have the ships, and you see the red dots here indicate where are the areas of very high traffic. And you see here in front of Portugal, there is a very high traffic, which is the ships that come from north of Europe and go to the Mediterranean. Here are the lanes that the ships cross, going southbound or northbound. And these are the traffic that comes from the Portuguese ports, which cross these lanes, creating conflicting situation with the traffic. So one can use the AIS data to study the traffic and to assess what is the main ship routes. So one can analyze the AIS data to identify the routes, to make trajectory prediction for ships, to assess the ships that are in collision, that have the risk of collision because they are too close. We can identify ships that have abnormal traffic when they go out of the main area, and also the risk is also assessed by studying in detail the accident reports where the influence of human and organizational factors is identified. So those are tools that we use to assess the risk of maritime traffic. Now, we have been developing different risks that look at aspects of the different conditions, like what increased weather conditions and human factors have on the ships. We have also seen the effect of the response to marine accidents, how the response has to do with the safety level. And more recently, work has been ongoing looking at the resilience of the marine transportation systems, of integrated systems, and also on the safe operation of autonomous vessels, so how autonomous vessels will fit into this maritime traffic. The use of the AIS data then allows them to characterize the patterns of traffic in coastal areas. This is Portugal, and you see what is here the traffic. The yellow shows a higher intensity as compared to the red. So identifying the areas with higher traffic. And in this way, we can also identify what is the probability of collision. The collision risk depends on the collision probability and on the consequences of collision. So the consequences can be the loss of life, can be damages to the ship and damages to the environment. However, the collision probability is what we want to reduce in the first place. This has to do with the number of ships that are present, and then multiplied by the probability that the ships will cause a collision. It is intuitively, it's easy to see that if you have many ships, then you will have a higher probability of collision than a situation that you have very few ships. This calculation of the probability of collision can be determined based just on the accident statistics by analyzing the statistics where collision have occurred, or you can build a model of the errors that can lead to collision, and this would lead to collision probabilities. And work has been done on both approaches to assess collision probabilities in different areas, mostly close to the coast. Now, the collision candidates, or the situations in which one can have a collision, are identified with a so-called safety boundary approach. This puts a safety boundary around the ship to indicate when danger of collision occurs, or just by looking at the absolute and relative speed and looking at what is the distance in the closest point of approach if the ship, if both ships continue in their trajectories. So this is the ship domain approach. Depending on the size of the ship and on the speed, we have a ship domain that defines the safety area around the ship. And when the safety areas start overlapping, then we have an indication that collision may be imminent or may become a problem. And when the ship violates the safety domain, then we have a critical situation as concerns the collision. We have been doing this type of studies in the Portuguese coast. This is an example of a case where we have these dots are cases where collision candidates have been identified. That is, ships where there was an overlap of this safety domain. And in general, we concluded that there are 55 candidates per day outside the Portuguese coast in this situation. Of course, in most of the cases, collision is avoided, but those are dangerous situations that occur. Now, we have, from the collision candidates, we have near collisions, which are cases in which the ship goes into the safety domain and then becomes very close to a collision. And from all these red dots of the traffic here, we have these blue dots, which are the cases of near collisions. So this can also be identified from the analysis of AIS data. And we can go a further detail and looking at the directions and identify the situations in which this happens. So these are the cases of overtaking, when one ship is overtaking the other one. These are when we have crossing, one ship crossing the path of the other one. And these are head-on collisions, so when the ships go in opposite directions and meet. And you see that all of those are identified. This system allows us to identify these situations. So we can then use these situations to identify the areas where we have the highest risks. And you see here them identifying the red will be the highest risk. This is Lisbon port. We have another port here in Setúbal. This is Sines. So it is at the entrance of ports where we have the highest risks, highest collision risks that are being estimated by this model. And this can also identify, this is the collision from all encounters, and these are just from crossing and from, we can also identify ship types. So this is the risk for tankers. We have different ship types. So there is, this type of study can be taken to different levels of detail. So all these tools that are used to study the safety of traffic of manned ships can now be used to study the mixed situation where we have manned and autonomous ships. And the concept that has been considered is to identify safe routes for future autonomous ship operations. That is to segregate the operation of autonomous ships from the mixed cargoes so that in the congested areas they are separated and it will be easier to manage the situation. So that's how we are dealing with the safety aspects. Just to close up, some brief idea about economy. I'm sorry that I'm going a little bit over time. The economy is the other aspect. There has been very few studies about the economy of operation of maritime vessels. I will give you two examples of the very few that I was able to identify in the literature. One case is a study that we made. It's a container ship transportation in Portuguese waters. So we are studying what is the economic feasibility of substituting a container ship by an autonomous container ship. So we started from the conventional ship and did some design changes to make it autonomous. So we maintained the main dimensions, the machinery and the equipment, and we thought of a 20 years investment period. This is the initial ship. It transports containers. It has 112 meters, so it is a relatively small ship. The route is from Lisbon to Porto, then to Açores. It stops in two places and then comes back. So it is a distance of 1,900 nautical miles. Which represents 120 hours of navigation. So we have about 2 weeks of the ship to complete the voyage. The changes made in the design are to reduce the superstructure, because not having men on board, we don't need so many living quarters, and this has been used to add additional space for container ships. So instead of 610, now it has 655 TEUs that it is able to carry. Now we consider that it's necessary to have a onshore center to make it more profitable. We consider that the fleet was larger than the ship, so there was a 4 ships fleet that would be monitored by this center. And the conclusions from this study is that the ship would have slightly more cargo capacity, so we increased the cargo capacity by 8%. There are several components of costs and voyage costs that decrease significantly, increasing the revenues. However, the remote center requires significant capital, and keeping the same investment return rate, the new building price of the autonomous ship would be about 1/3 higher than the conventional ship. So the new building will be higher. We have, however, revenues increase from the operation. So this was an exercise that gives some idea of the order of magnitude of costs involved. Another study was made with the bulk carrier. It was made a few years ago. And here they are comparing the operating costs of a conventional and an autonomous bulk carrier. And the comparison is made only on the operational costs, calculating the expected present value. 3 scenarios were considered: the reduced cruise, the adding a fuel efficiency in the sense that fuel is not used for onboard systems, and then a third scenario that the ship is being operated with diesel oil instead of heavy fuel oil, with the idea that heavy fuel oil is a complicated system to be operated without men on board, so this would be a more realistic one, but this is more expensive. So the results were this cost of the reference vessel. In scenario A, the cost was kept more or less the same. There was a slight improvement in scenario B, but in the last scenario with diesel oil, the costs were much higher. So this gives you some idea where we are with the economy. Not clear answers already. In some situations, savings appear to be possible. In other cases, it appears that it will be more expensive. So we still have to clarify this issue before having a final answer. So the overall conclusions then is that we have the basic technology for path planning, guidance, and control, although we need to make improvement in situation awareness and fusion of sensor data for short-range information. We still need to demonstrate that the safety level, which is the safety level associated with the operation of these ships. We have to demonstrate that the ships are economic from, they are profitable from an economical point of view, and we need to have regulatory framework to be able to operate these ships. So there is still a lot of research and a lot of work in front of us before this becomes a reality. However, the basic technology seems to exist, and it's a matter to work on it and to try to improve the situation. So again, I'm sorry for having taken a few more minutes than initially planned, but I'll be available for any questions now.
Okay, thank you, Prof. We have many comments, but we have some questions. I see here in the comments. We have the first one from Simman Singh. Dear Prof, what is your opinion on the possible misuse of autonomous ships? Ships technology. For example, in transporting illegal products like smuggling, drugs, and so on. And how do you prevent that?
Well, we have that problem with manned ships. So we will have that problem with unmanned ships also. There is no way to avoid that. It's a matter of inspections at the start and the end of the the voyages of those ships. It's a similar problem with manned ships.
Okay. I think you know Dr. Xiao. He has met you before. He just said
Yes.
thank you for your presentation. Nice topic, and he's still working on this ship collision risk study.
Very
Okay.
well.
And I think the next one is from Professor Afifi. I think you met him before, Professor
Yeah.
Afifi, when he came here.
Yes.
So he's always interested in this marine research. I think basically what he asked is that, we have a Penang ferry,
Yeah.
from the mainland to the island of Penang, and it goes back and forth, So that
Yes.
could be good autonomous application for the ferry. But he said there's one problem. If, it carries cars as well, cars on the ferry as well as passengers. Say one of the car, somehow the owner forgot to take the key, so he was locked from outside. So the car was cannot move, So
Yes. Yeah.
what happened with that, Say the
Yes.
ship
I
autonomously,
have. Yes, I have mentioned one example of a ferry. I'm sure that there exists other examples that this technology have been used, and I'm sure that there are many situations like the one you mentioned, which could be used to test some of the technologies. There is also another aspect that you have very close to your doors, which I have not mentioned. Close to in the Strait of Malacca is an area that you have very high traffic, and that you have also important problems of traffic congestion. So it's also an area of application and study that is very close to your location.
Okay. I think he got another second question. His final question: will local authority allow ship to berth with no local pilot on board? It means, can you do it without a pilot?
Yeah. Well, those are the difficult questions. The idea is that when the situation becomes complicated, we have remote control, and we may even at the beginning require the presence of somebody on board, but then you would need to have controls on board that could be operated by a person there. There are research and there is work on automatic berthing. There are already some advances in that technology, but of course the approach to the quay can be complicated and may require a pilot either on person or in remote control.
Mm-hmm. Okay, do you have one? Yeah, that's this one from Dr. Xiao. So it says here, okay, hi, good day, Straits of Malacca. I did mention Straits of Malacca and Straits of Singapore, very narrow. A lot of these ships around that travel from Straits of Malacca to South China Sea should need to pass this very short bend,
Yes.
So that's a short bend there. In this condition, how to decide the best route for the autonomous ship to travel?
Well, the best route will always depend on the situation at hand. What is the traffic at that precise moment? So this has to be a decision on a case-by-case basis. And I know that Dr. Xu has been doing quite some work in monitoring the traffic in that area. And in some sense, I would like to return back the question to him: how has he progressed in studying the traffic in that area?
Okay, I think you will answer that after this, Okay. There's another one from Dr. Yasin Adnan. He's our lecturer. He just joined as a lecturer. He graduated from University of Osaka, Japan, and he did some work with Professor Hasegawa. So
very well.
So he's interested in something autonomous, autonomous container ship.
Yes, yes.
I mentioned on the berthing.
Yeah.
Oh, yes.
Yeah, I believe you are mentioning this Yara Birkeland concept that I referred to. I don't know the details. I know the ship is being developed. I don't know the details on how they are planning to do the berthing.
Mm-hmm. Okay, another one. Is another one from Dr. Fitri Adi. He's a lecturer in University in Terengganu. Malaysia, Terengganu.
Yes.
His question is on autonomous systems solely involved with the technology, how to integrate this technology with the rules and regulation with the port authority.
Well, that is the topic that I referred. We need those regulations to be developed before one can use the vessel, and this is IMO is looking into that. Classification societies are looking into that. I imagine port authorities are also looking into that, and they are the ones that need to develop those regulations before this can become a reality.
Okay, I think that's all on the question. Maybe a final one from me. My thinking is, okay, how do we generate interest, especially with the younger generation, on having this autonomous ship? I'm just thinking on, say, having competition with building some autonomous model or something like that, to give the new generation confidence in this using of these autonomous ships.
Yes, I think in general the young generation will be, well, at least the one that is studying engineering will be keen in looking at these systems, and they are relatively easy to build, relatively simple models that are remotely controlled, and they can test different control algorithms and different propulsion systems, so it is relatively easy to build models at small scale that they can control and do, and this would be something to encourage. The difficulty we have found here, which may be easier to solve in other places, is to have a location that easily accessible to do those tests, with a lagoon or one place where it is easy to put these models and to test them. This can be complicated in some cases, but if you have access to this place, then this would be nice to organize competitions for students. Yeah.
Okay, thank you, Prof. I think that's it for the question and answer session. So before we finish, our Dean, Professor Rafiq, will give some closing speech. Professor Rafiq.
Well, not a speech actually, just to say thank you.
Okay.
So, thank you to you, Prof. Adi, for chairing the session, and my deepest thanks and gratitude to our distinguished speaker, Professor Carlos Guedes Soares, for accepting our invitation to speak at our distinguished lecture series. It is certainly an honor to have you with us in this program. And to all our viewers worldwide, thank you for watching this UTM Engineering Distinguished Lecture Series. We have many more lecture series for you, so do stay tuned. Until next time, bye-bye for now. Bye-bye.
Okay, bye-bye. Thank you, Prof. Thank you all.
Well, goodbye. It was my pleasure also.
Okay.